Okay, so here we are on 13.4, related rates. We start with example 13.20. A stone is thrown into a pond, causing ripples in the form of concentric circles that move away from the point of impact at a rate of 20 centimeters per second. Part A. When a circular ripple has a radius of 50 centimeters, find the rate of change of the circumference, the rate of change of the area. Okay, so we're going to do this one, letter A first. Rate of change. So what is the rate of change when we're talking about distances? Um, Rates of change in terms of distances are going to be distance over time. So for this type of problem, we are going to have to differentiate implicitly, but not for x as we have been doing, but rather differentiate implicitly for time. Very well. So here we have a little bit of information that they're giving us. First of all, they're talking about um, the ripples moving away from the point of impact at a rate of 20 centimeters squared. So the point of impact is going to be the center of the ripples. So the circles or the ripples are moving away from the point of impact from the center at a fixed rate. So that means a fixed rate of change for the radius. So that means that the radius with respect to time is changing at this rate of 20 centimeters per second. For part A, the question is what happens to the rate of change of the circumference when the radius is 50. So the radius is 50. Same applies to the circle's area. So let's do part 1. And we need the rate of change of the circumference. So normally circumference is equal to 2 pi r. But if we apply the derivative of this with respect to time, we are going to get an expression that gives us different rates of change. So in fact, the rate of change of the circumference with respect to time is equal to, and we differentiate this with respect to time. So we would have to use implicit differentiation with respect to time. So 2 pi is just a constant. So this would be just 2 pi. That would be the first or the derivative of the outside of this expression. But then I have to multiply it times r, or the derivative of r. So that's going to be the derivative of r with respect to time. So notice that this is this over here, the rate of change of the radius. So then we have what we need for the answer, because the rate of change of the circumference would equal 2 pi times 20. And notice that we didn't need the radius. So this means that you have a constant change in the circumference as well. And that makes sense because the circumference is dependent on the radius linearly. So this equals 40 pi. And because we're talking about a rate of change, it's going to be centimeters per second. For part 2, they want us to do the same, but for the area. So let's remember what the formula of the area of a circle is. The area of a circle is pi r squared. So let's differentiate with respect to time. So this would be the derivative of or the rate of change, let's say the rate of change of the area is equal to, and let's differentiate this implicitly. So 2 pi r times the derivative of the inside, which is r, right? So this would be the rate of change of the radius. Okay, So now all we have to do is plug in the numbers that we already have in order to solve this. So we know then that the rate of change of the area is equal to 2 pi times r, which is the radius at that moment. So that would be 50. And this times the rate of change of the radius, which we said was 20. So this is going to give us 4,000. No, not 4,000. 2,000. 2,000 pi. And because we're talking about area, 2,000 pi centimeters squared per second. So next, let's focus on part B. So for B, it says repeat part A when the radius is 100. So number one, we already said that the rate of change of the circumference was linearly dependent on the rate of change of the radius, and that this was not going to change anyway. So this is just going to be 40 pi centimeters per second. But for part two, because we found that the rate of change of the area is equal to 2 pi r. So r used to be 50, now it's 100. So 2 pi times 100 times the rate of change of the radius. And this equals 4,000 pi centimeters squared per second. Okay, people, so next we are going to work on example 13.21. And it says, a 4-meter ladder stands upright against a vertical wall. The foot of the ladder is pulled away from the wall at a constant rate of 0.75 meters per second. So that means that here we have a rate. So that means differentiation of the x direction in terms of time. So this is equal to 0.75, and that is the same as saying 3/4. Now I want it in fractional form, and you will see why in a bit. So the question is, find how fast the top of the ladder is coming down the wall at the instant it is A, 3 meters above the ground. So we're going to do A, 3 meters above the ground. So that's when y equals 3. But they want us to find the rate of change of the y direction. So that would be differentiation of y in terms of time. Okay. So how can we relate these things? How can we relate x and y and their derivatives, their instantaneous rates of change? The way to do that is to find an equation that relates these three things here in the graph. Now, obviously, that's going to be the Pythagorean theorem. So we know that x squared plus y squared equals 16 is a function that represents this situation at this moment. So if we do implicit differentiation on this with respect to time, what do we get? Well, we would get 2x here times differentiating x, because that is just part of the chain rule. So dx over dt plus, same thing with y, 2y times difference in y, or rate of change of y. And this equals 0 because 16 is a constant. Okay, so now what we really have to do is solve for this, because this is what they are asking us for, which is find how fast the ladder is coming down the wall. Then we have this here, y, but we know that y is 3 because they're asking for the instant when the ladder is 3 meters above the ground. So y is 3. The rate of change in the x direction, we already have it. It's 3/4 meters per second. X, we don't know, but we can put x in terms of y. right? Because x is the same as the square root of 16 minus y squared. So let's think of x as square root of 16 minus y squared. So let's rewrite all this, plugging in the values. So this would be then 2 times the square root of 16 minus 3 squared, because that's y, times 3/4, because that's the rate of change of the x direction, plus 2 times 3, which is y, times the derivative of y in terms of time, equal to 0. So notice that all we have to do is rearrange this equation and solve for this, right? The rate of change of the y direction. So if you do all that, you're going to get that dy over dt is going to equal negative square root of 7 over 4. And this is approximately, because they want us to give answers to 3 significant figures, this is approximately negative 0.661 meters per second. Okay. For part B, they're asking us, how about when it's 1 meter above the ground? So it's much easier just to plug in 1 here than to repeat the whole process, right? So here we did it for y equals 3, but now we're going to substitute the 3 with 1, and we can find out what was the rate of change in the y direction when the top of the ladder was 1 meter above the ground. So let's substitute that for 1 here. So this would be 16 minus 1 squared, and this would be 2 times 1. So again, and this is for part B, we would solve for the rate of change in the y direction, right? Or differentiation of y in terms of time. And this is going to be, in this case, equal to negative 3 square root of 15 over 4. So that's what we would get if we work on this equation when y equals 1. And this is equal to negative 2.90 meters per second. Now notice that it's a lot faster the closer it got to the ground, and that makes sense due to the acceleration from gravity. And notice also that these negative results make sense as well, because we're talking about a negative velocity since the ladder is falling down. Okay, so now we are on example 13.22, and it says in example 13.21, how fast is the angle between the ladder and the ground changing when y equals 2 meters? Okay, so that means that they want us to find the rate of change of the angle. So we have to use a trigonometric ratio that will help us out. Now, because they're giving us y, I want to end up using sine, because notice that y is the opposite leg from angle theta. So that means that I want to use cosine, because the derivative of cosine is sine. So cosine of theta is equal to x over 4, which we can use then to find the derivative of this, because that's going to give us the rate of change. Okay, so what's the derivative of this? The derivative of cosine of theta is going to be minus sine of theta. But because we're doing implicit differentiation with respect to time, we also have to do the derivative of the inside. In other words, apply the chain rule. So it's going to be negative sine of theta times the rate of change of the angle, which is what we want to find. And this equals 1/4, right? That would be the derivative of x over 4, because x over 4 is 1/4 x, times the derivative of the inside. So that would be the rate of change of x. Now, because they're talking about example 13.21, we already know what this rate of change is, because this rate of change is 3/4. So notice that we can plug in everything in this equation and then solve for the rate of change of the angle. So negative sine of theta, that's going to be minus y, right, over 4. But y, in this case, is equal to 2, as they said here. So negative sine would be 2 over 4, and that's 1/2. So negative 1/2 times the rate of change of the angle is equal to 1/4 times 3/4. Okay, so if you solve for the angle, or the rate of change of the angle, I should say, this is going to equal negative 3/8. That's going to be radians per second. Okay, people, so we are now on example 13.23, and this is going to be the last example on this video. So it says, consider a conical tank as shown in the diagram. Its radius at the top is 4 meters, and its height is 8 meters. The tank is being filled with water at a rate of 2 meters cubed per minute. How fast is the water level rising when it is 5 meters deep? So this is a typical calculus problem with related rates regarding a cone. So notice to the right here that we have that in a cone, you have a special situation. You have right triangles where you have similarity. So that means that you have ratios that are equal. And we're going to need this in order to solve the problem. You'll see why in a second. Okay, so the first thing that it says is that the tank is being filled with water at a rate of 2 meters cubed per minute. So that is a rate of change of the volume. So the volume is changing at a rate of 2 meters cubed per minute. Okay. We also know that the radius is equal to 4 when the height is equal to 8. And they want us to find how fast the water level is rising. So they want the rate of change of the height. So how far is this rising when the level of the water, so the height of the water, is 5 meters. So this is what we have from this problem. Okay, so because they're talking about rate of change of the volume, we should probably use the volume formula for a cone. And that is this one. So the volume of a cone is equal to 1/3 pi r squared times the height. Okay, but since they want us to find out the rate of change of the height, I'm going to keep the height, but I want to get rid or substitute this variable, which is the radius, and I want to substitute it for an expression that gives us the radius in terms of the height. And that's easy to do because we have this relationship here. When the radius is 4, the height is 8. So that means that radius over height is equal to 4 over 8, and that is really 1/2. So that means that the radius is 1/2 the height. So let's plug this into the volume formula. So we're going to get that the volume is equal to 1/3 pi times 1/2 the height, which is the radius, squared times the height, and therefore the volume is going to be 1/12 pi times the height cubed. So this is what we're going to use to find the rate of change of the height, which is what they're asking for in this question. So I need a little more room here. So let's get rid of this stuff that we did at the beginning. And we are going to work on differentiating the volume. So if we grab this formula and differentiate it with respect to time, we're going to get that the rate of change of the volume, is equal to, send the 3 to multiply, so we're going to get 3/12, which is 1/4 pi. 1/4 pi times the height squared, right? That's going to be through implicit differentiation and the chain rule. This is the derivative of the so-called outside. So this times the inside, which is h, and we differentiate h with respect to time. So then this is what we want to find right here. Okay, so they want us to solve for the velocity of the water level rising when the height is 5. So now what we have to do is plug in the information that we have. So we know that the rate of change of the volume is going to be 2 because the tank is being filled at the rate of 2 meters cubed per minute. So this is equal to 1/4 pi times the height at that moment, which is 5. So 5 squared times the rate of change of the height. So all we have to do is solve for this, like I said before. So what are we going to get? If we do the math, we're going to get that the rate of change of the height is equal to 8/25 pi, and this is approximately 0.102 meters per minute. Or if you prefer, approximately 10.2 centimeters per minute.